Welcome you all to section 7.3, special exponential functions. This is your boy, Mr. Bergman, here, coming to you not live, but I'm podcasting it, so here we go. This is review. Let's do something we've already done. What is the final value of a $1,000 bank certified deposit that gives 3% interest annually for 5 years? CDs are a really great way to invest. You give your money to the bank and they'll give you a predicted amount. It's not even market dependent, a predictable amount of money at the end. So 3% interest annually for 5 years. What that looks like, P is equal to 1,000, and the rate is 0.03, that's 3% as a decimal. And then for 5 years, the T is time. So we have a formula and the formula that we've been using, it's actually right up here in the previous thing, exponential growth. A is equal to P times 1 plus R to the T. That'd be P times 1.03 raised to the fifth power. And if you type all that into your calculator, you get that. So the next thing I want to know is, what do you know about pi? Pi is a really interesting number. It's irrational. So you can see pi is the kind of thing whereby, is there a pi button here? Yeah, there is. Pi button on the Inspire is right here. You can see it's right next to the H. You go control. No, you don't go control. You just press the pi button, and you remember I. You remember, there's an infinity symbol right here. So pi button is that, and you know that it's a decimal that it doesn't stop at the 9. It just keeps on going forever. And no patterns and no repeats. And it's a really important number that we use when it comes to circles. Anytime there's a circle formula, or you want to relate the radius to the diameter, or to the volume, or to the surface area, you've got to have pi in there somewhere. It just drops out as part of the formula. So it's irrational, meaning the decimal version doesn't repeat and doesn't end, and it's used in circle formulas. We'll need that for the second part of for the back side of this page. Compound interest. Here's another version of interest you can have. This was kind of simple interest using this formula here, but this is going to be compound interest. What does that mean? So what they can do in a bank is they can give you not your interest all at once at the end of the year, but they can give it to you every half year, for example. So they give you half your interest. If you put it in January, then they'll give you half your money, half of your interest in June or July, and then again at the very end of the year in December, they'll give you the rest of it. So what you have to do is, if you're getting 6.5% semi-annually, that means you take the 0.65 and you cut it in half, because you get half in June and the other half in December. And then because you're being given interest twice, you have to multiply not once but twice. So if T were equal to 1 year, then you're actually getting two investments. You start with $1,000, and then you multiply it by 1 point, half your interest in June, and then multiply it again by 1 point, all of your half your interest in December. The formula looks like this. It's a little tricky to think about, but basically you can see what's new is there's an n over here and an n up here, and n is just the number of times that interest is compounded per year. If you semi-annually means twice a year, so 2 over here and 2 up here. Quarterly means here there would be 4 times. So every 3 months you're going to get a quarter of your interest, but it'll happen 4 times. If you get it monthly, you get 1/12 of all of your interest 12 times. And actually, there's more money to be made the more often you compound it like this. What I want to do is think about what it might look like to increase the compounding periods. So here we're starting with only 2 periods here, and now 4 periods, and then 12 periods. So the number of compounding periods starts at 1 if you're compounding it annually. 2 if you're getting your interest twice a year. 3 times would be every 4 months. Then 4 times a year, then 5 times a year, then 100 times a year. What about if you got interest 365 times a year, like compounded daily? Or every hour you got a tiny fraction of your interest every hour. You're actually going to make more and more money, slightly more and more money every time you increase the number of compounding periods. Let's hold everything else the same and only increase the compounding periods to compare. So let's just say you start off simply with just $1, and it's going to spend 1 year in the bank, and there's a 100% rate. So pretty much all these variables are going to be 1, and t equals equal to 1. The only thing that's going to change is n, the number of times interest is compounded per year. So you can see if you start off with just if you're getting once in a year, that's going to be 1 plus 1. This is all going to 1 plus 100% is going to be the same thing as 1 plus 1, which is 2. So the growth factor here is going to be 2, and so you can see you get $2 at the end of the year. You started with 1, double it to get 2. But if you're going to do that, if you're going to change it to semi-annually, it'll be 1 plus 1 over 2, like 1.5 times itself twice. 1.5 times 1.5 is going to give you 2.25. So you're actually making more money if you get half your interest in June and half your interest in December. And then, as you can see, as you increase the number of compounding periods, you're going to get more and more and more money, marginally, just a little bit more. But it's not. You can't go as high as you want. You can't just like compounded hourly is better, but compounded every minute is even more money, and compounded every second is even more money. But it's not going to go up to infinity. You can't just like, as you increase the compounding periods, it's going to approach a certain number. And the number that it actually approaches is 2.71828182884. And we're going to give, that number is actually so special. It might sound kind of weird and strange now, but that number is so special that we give its own letter. I don't know if you've ever noticed this, but we solve equations that have x's in them and y's in them and z's in them and then t's in them as well. But you've never, in all of Algebra 1, pre-algebra, or Algebra 2, have ever had to solve an equation e, what is e plus 2 equal to 5? That's never an equation, because e is designated as special value and role in mathematics. It's so incredibly important that we've never actually solved an e equation, because e is going to be now equal to this. Pi is equal to this, e is equal to this. And e is going to actually serve as a very similar role. This number here, e, is where the dotted line is exactly. It's the number that you'll never quite approach that. If you increase the number of compounding periods, you will approach but never cross e. E is going to be irrational, just like pi. It's going to be used in lots of exponential formulas. So often that by senior year, I know it's strange right now, but so often by senior year, you're actually going to be glad to be using e instead of, say, a base like 2 or base 10 or whatever. E is going to be the center of the exponential world by the time you finish your senior year. So let's get used to it now. If you're wondering what is e, you're like, Bergman, what is e? Well, it's kind of like pi. It's a very specific value. It's a number, and it's an irrational number. So what happens to the growth factor as n increases? As n increases, the growth factor is going to turn into e, which is approximately 2.718, but is exactly, a number that we can't express. You can even type it in a Desmos. Just type in the letter E in a Desmos and hit enter, and it'll tell you, well, E is 2.718. E is so special. It has its own button on the Inspire. Check this out. It's not even like a shortcut. It's not even in a menu. It's not even tucked away. We're going to be using this button so many times, you're going to wear it out. So check this out. E, just press it once, and then you can E. It already knows, it's because it already gives you an exponent. E to the first power, enter. 2.71828, approximately, it rounds, just like it rounds pi. Okay, so that's what E is. What is E? It's a number, 2.718, approximately. So there's a formula. If you wanted to talk about continuous compounding interest, meaning compounding at every single conceivable moment, not just daily, not just hourly, not just by the minute, not by the second, not by the millisecond, but if you wanted to compound interest continuously, always getting more and more interest, then you can use E here. You notice the formula gets way simpler, not way simpler, but a little bit simpler. P times all that raised to the just, like, compare this formula to this formula here. There's just fewer formulas, and this E is a decimal. So you have an input of P and a rate and a time right there. So let's actually do this. Compound interest. Tatiana deposited $1,500 in a savings account that gives her 2.5 annual interest compounded continuously. If you see this word continuously, that means you have to use the E. After 4 years, what will the balance be? All right, so let's just type it in. 1,500 times E. There's the formula. 1,500 E raised to the, let's see, R. What's the rate? It's 0.025 times the time, 4 years. Enter. You can see this is, it's going to give her 1,657. Notice we don't even need to change this. We don't need to add 1. It's just going to say 0.025 because that's the rate. There it is. Compute each to 4 decimal places. All right, so let's just get practice using the E button. So E to the first power is there as we got it, rounded to 4 decimal places. 1, 2, 3, 4. So I'm actually gonna show you how you can make the calculator automatically round. We'll go back to 5 settings, and then 2 document settings. I want not float 6, but let's go. Oh, this is not gonna work perfectly. If you really wanted to, you could type out round on the home screen, and then type in E raised to the first power like it's asking you to, and then I'm going to go to the next and exit the exponent and type in a comma, which is right down here, comma, and how many decimal places. You need to tell it 2 things separated by comma. Tell it the value that you want to look at, and then how many decimal places you want rounded, and it's going to round it for you. 1, 2, 3, 4, 2.7183. So you can use it if you want. Let's get round. Let's round E to the third. E raised to the third button. Exit the exponent with the arrow, comma, and then raise it to the 4th. Round it to the 4th decimal. You can see there it is. I'm going to actually press the up arrow. I don't feel like typing it in a whole bunch of times. I'm going to type this in just once. And now I'm going to change negative 0.23. And there it is. E to the 0, anything to the 0 power is 1. And so here, what we can do is we can type in, I'm only going to type it in once. So this is an exponent of 1 plus 9 is 10 minus 3 is 7. So up, enter, and 7th. There it is. All right, and so then E to the 7th is going to be that. Let's graph it. You can see here's the base. The base used to be numbers like 2 or 3 or 1/2, and now it's just going to be E. Remember, E is just a number. It's 2.7183 approximately. And so and that number approaches right. E to the first power is this right here. We can even graph it like this. Let's press this button right here to toggle it back to the graph. Let's press tab to get F1, and we're going to say it's E button and then X. And then enter. And there's the graph. Let's take a look at the table. Control T for the table. And so there's E to the first power there's the E written as a decimal, and then if you square it, this is this, and if you cube it, it's this. And it goes up pretty quickly. In fact, as x approaches positive infinity, this is going to approach positive infinity, and as x approaches negative infinity, then the value of the function is going to approach 0. And you can see that on the green graph right here. The green dotted line along the x-axis, very similar to when the base was 2. And just like when the base was 2 here, if we do a vertical shift of -1, all these y values get 1 less. This used to be 7.39, now it's 6.39. And even though the asymptote right here, the dotted line that shows you what it's going to approach, is going to be down at -1, where it used to be at 0 here. If we're going to have a horizontal dilation of 2, that means it's x divided by 2 on the inside. E to the x divided by 2 is going to be all these numbers right here. You can see it's going to be twice as far away from the y-axis. You can multiply, over here, you could multiply the x values by 2 and still produce the same the same values that you got over here. So when here x used to be 2, and if you were to plug in, but here the x values got multiplied by 2 to get 4. So if you plug 4 in here, it's e to the 4 over 2, which is the same thing as e to the 2. It's 7.39, 7.39. But as you can see, all these values got, all these x values got doubled. So I want to know if you can figure out if x is equal to 0, plug it in here, what's the y value going to be? Let's talk about e. As a function, e to the x, it has all the same transformations as before. You've got a vertical shift, vertical dilation, horizontal shift, x minus a, and horizontal dilation. The domain, just as before, is all real numbers. The range is from 0 to infinity, not including 0. It does pass the vertical line test. It does pass the horizontal line test. It has no x-intercept. The green one does, at least because it goes as close as you want to the x-axis, but it'll never cross it. The y-intercept is 1 right here, and as x approaches infinity, the function is going to approach infinity. As x approaches negative infinity, it's going to go to 0. That's symbolized graphically here by the asymptote. And is it increasing or decreasing? It's only increasing from negative infinity to positive infinity. There's no symmetry. You're welcome. Take care. I'll see you in class. And I just wanted to say that my favorite comedy of all time is Monty Python and the Holy Grail. I basically spent all of middle school pretending I was in Monty Python and the Holy Grail. It's a really funny movie from the 70s, and it's just my kind of humor. I want to know what your kind of humor is, and I want to know if you've ever seen Monty Python and the Holy Grail. Take care, and I'll talk to you later.